Today we start one of the most important concepts in electrodynamics, the electric field. Alright, these photos, which are drawn from your textbook, show the iron filings make a pattern they make when sprinkled around a magnet. These patterns suggest that space itself, your textbook is very proud of that, space itself is filled with magnetic influence, which we call the magnetic field. The concept of such a field is introduced by Michael Faraday in 1821. This is a little bit of a bizarre aside because in the end we're not going to talk about magnetic field, at least not right now. We're going to talk about electric field, which is an analog to it, and we'll see patterns that kind of look something like this, and we'll talk about what they mean. It turns out that what we discover for electric fields will then work for magnetic fields as well, and will make them much easier to understand. Some technical definitions. A field is a function that assigns a vector to every point in space. So what would be a field? Well, for instance, if you think about the wind blowing, the air's velocity at any point in space is a vector field. We should be a little careful here because your textbook is a little aggressive and I should have fixed it. A vector field is a function that assigns a vector to every point in space. You can also have scalar fields that assign scalars to every point in space. For instance, the temperature at every point in the room is a field, a scalar field, and the wind velocity at every point in the room is a vector field. So field in general just means a function that takes as its argument a position in space and gives you a value back. We've run into one that we've used obliquely and incidentally, but the alteration of space around a mass is the gravitational field. We've talked kind of that word, it comes up a bit, and we don't talk that much about it because it's not a particularly intuitive way of handling a relatively simple thing, but we could have talked about it. We could have said that if you have a mass, then anywhere around that mass, space is bent so as to attract things towards that mass, and that the Earth puts out, for instance, a gravitational field that does that. And finally, the eventual payoff, the space around a charge has an alteration in it which creates something called the electric field. All right, it's the mechanism through which the charge expresses its electric influence on the rest of the universe. It is, and I'll warn you right now, kind of abstract, and it's not going to be able to make it less abstract. We'll have some hand-wavy things, but it is in fact the next level up in your mathematical abstraction for understanding physics, but it is tremendously powerful. Here they have a model of it. They'll say, if we have a force that A is attracting B with, force A on B, in the Newtonian model, this is just a force. A exerts a force on B. But in Faraday's field model, A changes space around it somehow. Though, as they say here, the wavy lines are poetic license. We don't know what the alteration looks like, but somehow space has been made different, has been altered because of the presence of this charge. And then particle B is moving through that altered space and therefore responds to it in such a way in this particular thing as to produce a force which points this way. So we've taken this direct interaction and we've mediated it with a field. In fact, we'll often talk about mediation by a field. Media is between in Latin. Like medium is between two extremes, or the news media is between you and the news. And here mediation means literally the field is between the two particles. It's what conveys the influence. All right, if we take a charge Q, which we call the probe charge, which means just a thing we're allowing to move, but is so small that it does not itself produce significant forces on other things. If we move this thing around and we see that it experiences some electric force, then we say, in other words, we declare that there's an electric field that is causing that force, and the electric field is defined as indicated here as the force felt on Q at that position divided by the size of the test charge. So you're like, why do we do that? And part of it's because we're saying that the effect should scale with the charge. So we'd like to get independent of what we bring in. We know that, for instance, from Coulomb's law, it's the product of the two charges that matter. So if I have a charge Q1 and I want to talk about its effect on things, I don't want to have to include what it's affecting. I want to say that it produces a certain electrical influence. And so we divide out that extra charge. All right. The units of the electric field are newtons per coulomb. Why? Well, really as simply as newtons per coulomb. Like, duh. The magnitude E of the electric field is often called the electric field strength. Although we'll often just say the electric field is this. We really mean how strong it is. It works the other way. If we know the electric field, then we can figure out the force on a charge in that field by simply multiplying by the charge. That the force on some charge is just the charge times the electric field. If we know the field, we can do this. You'll see that that is really just the inverse of the first one. All right. If Q is positive, the force on the particle is in the direction of the electric field, and the force on the negative charge is opposite direction of the electric field. And although, again, your textbook acts like that's really deep, it's really saying if Q is a positive number, then the vectors are in the same sense. But we know if Q is a negative number, what negatives do to vectors is flip them. So it's nothing deeper than that, and it isn't really worth its own page, but it gets it. All right, to sum up, if I can measure the forces, then the electric field is the force divided by the charge at every point. So we probe it with a bunch of little charges, or one little charge we move around, and the electric field is the force over that charge. On the other hand, if I know the electric field and some other charge Q, then I can figure out the force on Q by multiplying Q by the field. All right, the charge rescales the field to give us a force. Michael Faraday, who's an interesting guy, started off completely poor and broke and knowing very little, went to see a lecture at the Royal Society and was enthralled by, sadly, chemistry, but he was pretty broad-minded, so it was okay. And made a deal where he would sweep up and clean up the lab as long as they would let him learn science from it, and eventually rose to being one of the foremost experimenters in the world at that time. One of the things that comes from that is that Faraday was not mathematically trained. Faraday had basic grasp of algebra, and that was probably more or less it. Everything else was very ad hoc. As such, he came up with very intuitive, non-mathematical ways of looking at things, and some of them are so useful we still use them 2 centuries later. For instance, his rules for drawing field lines. His concept of field, he said, field lines start at positive and end on negative charges. That's the first thing. They flow or point from positive to negative. He was imagining them actually as the direction of some sort of current of liquid. In Faraday's time, people thought the electric charges weren't discrete points, but were rather some sort of liquid. And there was a positive liquid and a negative liquid, and the field lines were really just the flow lines of that positive fluid. We don't use the fluid mechanism anymore, but some of it still kind of hangs out in our terminology. Number 2, the field lines are arranged such that at any given point, the force felt by a positive charge is tangent to the field line at that point and points in the same sense. And thirdly, the visual density of field lines is proportional to the strength of the electric field. Where field lines are packed close together, the field is stronger. So putting all of that together, if we were to someone say, this is our electric field, then we would say a couple things. If I were at this point, I would feel a force, a positive charge would feel a force that was tangent to that point. So that's the force. And these are the electric fields. And here the assumption is that Q is positive. If Q is negative, it feels a force pointing the other way. We've already talked about that. All right? We really should say these field lines are starting and ending from things. So Faraday would say they all start on positives and they'll end on negatives. And then lastly, Faraday would say where they are dense is large electric field, but where it's sparse, so roughly the same size but only get one line, is low or weak electric field. All right, and don't get over emphasized on that, but mostly we're saying where things look dense, the field is strongest. So take a look at this one. 2 protons, A and B, are in an electric field, as given. Which proton has the larger acceleration? Note here that the positive and negatives generating this field are not drawn. That's very traditional. They're just outside the window. They're way off somewhere. It doesn't really matter. They produce a field which looks like this. All right, they're both protons, which means they both have the same positive charge. Positive charge means that they'll accelerate along the field line. So they both get forces that look something like A is accelerated that way and B is accelerated that way. But we can see that the field lines are much denser. We take the same size. The much denser around A. So A has a stronger field. And since the force is the charge times the field, higher field means higher force. Proton A feels the greater force. All right, a proton is moving to the right in a vertical electric field. A very short time later, the proton's velocity points in which direction? Again, remember, being a proton and being positive, it's going to feel a force which is upward. So it's going to gain some amount of velocity which is upward. They say a very short time later, meaning not a lot of time for it to gain that velocity. So our actual net payoff here is like that. So it looks like more over than up. That would seem to be case C. Now, as time goes on, it will continue to accelerate upward, and so this will change. But we'll talk about that one later. All right, which electric field would be responsible for this proton's trajectory? We see that the proton is undergoing a parabolic trajectory, and that says to us, well, parabolic trajectory is constant acceleration, which means constant force, which means constant field. So I need the field to be constant. That immediately turns out these two, because the fields aren't constant. The acceleration is pointing towards the right, so the force has to point towards the right, so the field has to point towards the right. That kills that one and that one, leaving us, not surprisingly, with the one in the middle here. A constant field that points rightward and therefore drags the proton rightward. All right. For the rest of this, we're going to talk a little bit about some given fields, ones you need to know. And the most important, the foundational one, is the electric field of a positive point particle, like a proton or other positive point thing. And it looks like this. It radiates away in all directions. And then, now this is not a field diagram, this is a electric field line diagram. Let's not stress over that. The electric field diagram would be the following. Oops. Right? This is what's called a force vector diagram or field vector diagram. If we're going to draw an actual field diagram, well, it would point like that, and like that, and like that, and like that. And we might put at the 8s, right? So we get 8 of them. We could draw any ones we wanted, but the key thing is that it is getting less dense as we move out along here. So that's showing us that the field is falling off. Here, they're actually drawing the length of the field vectors, so we show them falling off directly. You might have noticed, if we look over here, what does the field look like? Hey, it's that weird 1 over 4 pi epsilon. We're kind of stuck with that. And then Q over R square. And then this weird thing, R hat. R hat is the unit vector pointing away from the charge. So it's a thing which is of unit length 1, and wherever we are, it points away from the charge. These are all R hats. What does this end up looking like? Hey, that looks a lot like the Coulomb forces, and of course it has to, because remember the force would be Q times this. So we took some other charge, big Q in, we get the force between them would be big Q times little q over 4 pi epsilon naught times 1 over R squared. So it's exactly what we knew from Coulomb. And not surprisingly, this gets the, I think, relatively obvious name, the Coulomb field. The electric field of a negative point particle, hey, that looks a lot alike, right? It's basically the same thing. It has the same field strengths, and we probably should be well, we don't need to put in the minus sign. The negativity of Q is going to flip the sense of that, and so have them point inward rather than outward. But otherwise it looks the same. Again, for a negative particle, the electric fields will point inward. Remember, electric field ends on negatives, so they point in like this. We again can see the density argument working, and we still get what we want. This is a negative Coulomb field, and we'd still call it just a Coulomb field. All right, which is the electric field at the dot? So at this location, what field does this point, this negative charge, create? Well, we know that the field lines everywhere around the negative look like this, including this way. So this charge is going to move in direction B. By the way, this is going to be a little sloppy here. A positive charge located here would move in direction B. The field is the direction that a positive charge is accelerated. Of course, we're not surprised. A positive charge should be attracted towards the negative charge. All right, in which case would the electric field be greatest in magnitude? So remember, the electric field is 1 over 4 pi epsilon naught times Q over R squared in the direction of outbound radii. So if we take A to be our standard guy, that one is Q over R squared. And then point B would be 2Q over R squared, which is twice A, so A is now losing. Point C is Q over 2R squared, which is 1/4 Q over R squared. So that's even worse. And then point D is 2Q over 2R quantity squared, which is 2 over 4 Q over R squared, or 1/2 Q over R squared. So the strongest one is B.